Okay, so what is machine learning? Well, briefly, it's given a set of features, x's, we want to predict the outcome y. I'll mostly be talking about supervised learning and at times relating it to characterization prediction. There's two types of supervised learning. Regression, where we want to predict a numerical value. So let's say we have a memory described by its words, bits, and muxing. We might want to predict its time or power value. Then there's classification, where we want to predict one of a few outcomes. Again, let's say we have SPICE models, voltage and temperature. This time we might want to predict whether a circuit's going to pass or fail. There are several machine learning algorithms that can solve these problems. Over the next few slides, I'll describe a handful, give some pros and cons. But unfortunately, there's no magic bullet, or as they say, no free lunch. Many of you probably have experienced the use of lookup tables for maybe use in characterization estimators or fast SPICE simulators. Lookup tables bear really close resemblance to a machine learning algorithm called k-nearest neighbors. But there's other algorithms that can perform even better, particularly when the data is complex. Areas where I see machine learning having the most potential in EDA, I think Solido has already proven it with their variation-aware designer, high sigma analysis. They've been using machine learning for years here. But fast SPICE simulators, maybe we can replace those lookup tables with a more continuous learner. An area I'm most familiar with, characterization, where we can use it for memory or logic gate, power estimation, or timing estimation. Doing this will reduce the uncertainty or the padding that people like to apply and ultimately give you a more competitive product. I was able to leverage machine learning to create a tool like a memory selection tool. So if you have really accurate estimation, you can create what I call this efficient frontier of memory selection. So the graph's a little hard to read, but basically what it is for each dot represents a portfolio of memories for a given area power trade-off for that chip. Now, when people select memories for the chip, they usually end up somewhere on the interior of this graph. And they're not going to have the most efficient selection. So let me start the survey of machine learning algorithms describing one I've already mentioned, k-nearest neighbors. The way this works, basically you have a bunch of golden data that you've stored in a database, and when you want to make a new prediction, you query this database, find the closest matches, nearest neighbors, and return, say, the mean or the weighted mean. Now, while this method's pretty intuitive, easy to understand, it suffers from what's called the Curse of Dimensionality. What that means is, as your input features grow, your golden data needs to grow exponentially. Here's a plot of a prediction using a k-nearest neighbor model on the left. This is predicted versus actual data versus an advanced machine learning model on the right. The one on the right is clearly what we want to achieve, where all the points line up on the line. Next, a model that people are pretty familiar with, I would suspect, is linear regression. And this actually can do a pretty good job if following conditions are met. The feature space is rich enough. What that means is often we need to derive additional features through interactions or other basis functions to model nonlinearities. We should standardize our inputs. What that means is make sure the inputs are all of a similar range. And we should also use regularization for feature selection. Now, unfortunately, most of the time these things aren't done, and linear regression doesn't perform very well on new samples. Next one, decision tree. I think people are pretty familiar with this. Think of the game 20 questions. Pretty intuitive algorithm, although often it's too simplistic to model the complex data. Like linear regression, can do well on the training data, but not so good on the new sample data. Now here's a model that actually will perform pretty well. It's actually it's called Ensemble Method. It combines many learners into a meta learner. So it'll often improve the accuracy on new sample prediction, which is our goal after all. Examples of ensemble methods include bagging or random forests, and also boosting. The downside to this one, though, is the models can be pretty large, so if you need to persist it, the disk space required can be substantial. And of course, I'd be remiss if I didn't mention artificial neural networks or deep learning. This is everyone's favorite buzzword. These are excellent at finding those undiscovered features to model those nonlinearities. But it's a black box. It's hard to interpret. It can take a long time to train. The upside, though, is once you have a model, you can persist it pretty compactly on disk. So here's a summary table of a memory leakage prediction using the 5 models I just talked about, roughly ranked from worst performing to best performing for this example. The 2 at the bottom in green, Ensemble and neural networks, performed the best by far. You can kind of see that by the metrics in the middle columns. Now, before I talk about my experience with Solido's tools, I wanted to actually take a step back, give a little background on why I do believe in their approach. About 5 years ago, I became interested, most would say obsessed with machine learning. I created a machine learning-based characterization estimator, which was much more accurate than our existing KNN estimator. Out of that came 2 pretty cool tools. The first was a memory selector, which, let's say, given a physical memory words and bits requirement, it would return the best candidate out of thousands of choices. Following on that, I created a memory optimization tool, which is describing a chip in terms of its logical memory. So all the memories on the chip, it would return the best combination of physical memories. Now, this resulted in huge area and power savings for the chip teams. That actually made them pretty happy, as you can imagine. And about that same time, I had a really good discussion with Jeff Dick, who you'll hear from in a couple talks, about Solido's FFX regression technology. So the technology they use called FFX is basically a form of regularized linear regression with a bunch of crazy feature engineering. And I mean a bunch. It was actually very similar to the first machine learning models that I developed for my estimator. So, kind of with that inside knowledge, I really became 100% sold on their methodology. So here's some hands-on experience I've had with their tools. Their high sigma Monte Carlo tool, which I've used for bit cell sense sample critical circuit analysis. I've used both modes. They have a regression mode, which is when the output variable is continuous. You want to say predict bit cell current or sense amp differential. And also the classification mode when you're looking for a failure boundary, such as bit cell stability. This tool is absolutely required for design sign-off. Another, I'd say, must-have tool for memory design is the hierarchical Monte Carlo tool. So in memories, we have circuits that are 3 to 4 sigma problems and up to 6 to 7 sigma problems. And with this tool, you can basically verify the entire circuit without over-design. It's much less pessimistic than having to verify the entire critical path to the bit cell 6 to 7 sigma requirement. And finally, one of their newer tools called ML Car. This really is similar to the work I've done in the past, but on a much grander scale. It's one of the things it can do is say corner prediction. So given a set of basis corners, it can fill out the corner portfolio, basically saving days and days of simulation time. Other potential applications for this tool, I think, are slew load table population, or even creating a standalone estimator, or filling out that existing lookup table estimator, but at a much finer grid. And that's all I have time for. Thank you.